expressing the concentration of solutions. Now recall what a solution is. If we mix two chemicals together and the resulting mixture looks the same throughout, in other words, it's homogeneous, it's called a solution. And there are going to be some different ways to express the concentration of a solution. So it's important to know how to do that, how to convert from one set of units to another set of units for concentration. How do you prepare a solution? There's another good question. So these are good skills to learn that we're going to talk about and hopefully learn today. And if you do it wrong, the effect can be pretty dramatic, right? Especially if you work in a medical laboratory. So in the first place, what is the difference between a solute and a solvent? Our solute in this case is going to be our drink mix. And I'm going to monitor the concentration of the drink mix in the water. So if I add more water, right, well, the concentration stays the same. There isn't any drink mix. But if I add some drink mix, concentration goes up. Right? The concentration of the drink mix goes up. If I add some water, what will happen to the concentration of the drink mix? It will go down. Yeah, it gets diluted. So how do you tell, though? How do I know that the drink mix was a solute? Whatever you have the most of, that is always a solvent. It doesn't matter, solid, liquid, or gas, whatever you have the most of, and it will always be the solvent. Everything else, whether it's a mixture of 10 compounds or what, you just pick the one that you have the most of, that will be your solvent. What is going on at the atomic level when sodium chloride dissolves in water? Remember, sodium has a plus charge. Chloride anions has a negative charge. That's what holds it together, right? These ionic bonds. Well, we dissolve salt in water, right? It dissolves. What's going on there? Okay, so here's our salt crystal, okay? And you can see the water molecules floating around. Let's see if we can figure out whether the green or the gray spheres are the sodium ions or chloride anions. Let's see if we can figure it out. Okay, so the water's striking the salt crystal. Let's see if we can find something odd going on here. Here's something that's going on. Let's pause this. The oxygens of the water molecules orient themselves, right, in this fashion around that gray sphere. So that gray sphere has to have what charge? Oxygen's electronegative has a partial negative charge on water because it's polar, right? That gray sphere has to have a positive charge. That must be the what ion? Sodium ion, right? So sodium dissolved in water is hydrated or solvated, and the water molecules orient themselves around that ion in this fashion. All the oxygens orient themselves towards it. How about a chloride anion? For the chloride anion, the hydrogens had better. There they are. Right? Here the hydrogen atoms orient themselves as close as they can get to the chloride anion. So this is what a hydrated chloride anion looks like, or solvated. When we write AQ, right, as a little subscript, this is what we mean. We mean hydration, solvation. So from that animation, sketch what a hydrated sodium ion is believed to look like in water. So let's just draw a sodium ion. And remember what was oriented towards it? It was the electronegative oxygens. So just draw a sodium ion, and then a whole bunch of water molecules oriented around it. But the oxygens have to be close to it. And with the chloride anion, right, now the hydrogen atoms, the water molecules are oriented towards it. So this is what we call hydration or solvation. The little AQ that we wrote as a subscript That's aqueous, solvated. Would iron 2 or iron 1 be more strongly hydrated in water? And why? Does it make a difference? Well, sure. This has a much stronger charge. So that attraction would be a lot stronger, right? It's a higher charge, a greater charge. What is going on at the atomic level in a saturated solution of sodium chloride? So what's saturated? Remember, it just means no more salt can dissolve. You have a pile of solid salt on the bottom of the beaker. It just won't go away. What's going on there? So saturated solutions are in a state of dynamic equilibrium. Dynamic means both ways, right? It's dissolving and it's precipitating all at the same time, but at the same rate. It's dissolving at the same rate as it's precipitating. So they're trying to say, here's a hydrated ion, right? So here it's getting put together and getting taken apart at the same rate. So the animation isn't that great, but they're trying to say that this crystal of salt, right, it's precipitating, it's getting put together at the same rate as it's dissolving. So that's what a saturated solution looks like. What is the difference between a saturated and a supersaturated solution? This is an example of a supersaturated solution. It has a lot more sodium acetate dissolved in this bag than there should be dissolved. It's kind of like a sponge holding more water than it should be able to hold. It's a very unstable situation. They prepared this supersaturated solution of sodium acetate by heating water and dissolving a lot of sodium acetate. Heat it some more, dissolve more sodium acetate, right? Because the hotter the solution, the more it can dissolve. Then they let it cool down without shaking it and without any hygroscopic nuclei being present. And then the solution it should have precipitated out, but it didn't. It's holding much more material, much more sodium acetate than it should. So to prove that to you, you could break this bag open and stick some little particles in there, and it's all going to start precipitating, or you can push this little button. So when I push this little button, the precipitation just happens very quickly, and it starts feeling hot. So that is an example of a supersaturated solution. Now it's a solid, it's nice and hot for hand warming, and then you can regenerate it just by throwing it in some boiling water. We have 4 ways to express the concentration of a solution, and I'm going to give you these 4 equations. You just have to know how to use them. So here's the first one: molarity, symbol capital M, moles of solute over total liters of solution. Mass percent, the unit will be percent, and that's just the mass of the solute divided by the total mass of solution times 100. Molality, that symbol will be little m. Moles of solute divided by kilograms of solvent is how you get molality. And then the 4th way to express concentration is mole fraction. It's just a fraction, so the units cancel. It ends up being unitless. So it's the moles of A over the total moles. So if you want to find the mole fraction of anything, divide its moles by the moles of everything, and you get its mole fraction. Let's take a look at our first question here. How would you prepare 250 grams of an aqueous solution that is 10% sodium carbonate by mass? Now this how would you prepare part, we'll get to that. Let's just see if we can answer the question first here, what we need to know. The equation that we're going to use, the concentration equation, would definitely be this mass percent equation, because it's the only one that has percent in it, right? So 250 grams of an aqueous solution, well, that must be the total mass. So that'll be 250. And then it's 10%, so that means this must be 10. So we just need to solve for this. And that solute is what? Is it the sodium carbonate or is it the water? All right. It says that it's aqueous, so it's just understood that water is the solvent. Whenever they say aqueous, water is always the solvent. So when we find that mass of solute, we're actually finding the mass of the sodium carbonate. Okay, so let's go ahead and make our little equation, see if we can figure it out. We'll have then 10 would equal the mass of the sodium carbonate divided by, so when we want to solve for mass of sodium carbonate. So pretty much just leave the mass of sodium carbonate on that side, right? Do you remember doing this sort of thing? Whenever you want to bring something from one side to the other, just go along the diagonal. So it'd look like, and if you get used to doing this, do it all in one big step, man, it really helps. Okay, this is what I'm after. I want to solve for that mass of sodium carbonate. So let's just leave it alone. We'll move the 250 up to the top, move the 100 down to the bottom, and we'll have it. So you always go along the diagonal whenever you want to solve for something. All right, to go up and down. You're going to move something from one side to the other. So my mass of sodium carbonate would be 10 times 250 divided by 100, about 25. Okay, so, but the question was, how would you prepare? So you have to say, maybe on a balance, on a mass balance. So this is the how would you prepare part. On a mass balance, add 25 grams of sodium carbonate, then add water until 250 grams of solution is reached. Okay, or you could say, I guess another possibility is 25 grams of sodium carbonate plus 225 grams of water. So either way would work. All right. How many grams of hydrogen bromide are in 25 mils of aqueous 0.18 molar hydrogen bromide? The big M, when you see it, you're supposed to say molar. Molar. So we use our expression for molarity then, big M. Here it is. Big M equals moles of solute over liters of solution. Okay, so what do we know? Well, we know what big M is, that's 0.18. We know the liters of solution, that's 25 mils. We're just going to solve for moles of solute. Solve for moles of HBr. But they wanted the final answer in grams, not moles, so we'll have to convert to grams. So this will be a two-step question then, two-step answer. So let's go ahead and plug it in here. We'll have 0.18 has to equal moles of HBr over liters of solution. And what you can do is, remember, if you have, you just have to move the decimal place over 3 places. 1, 2, 3. 0.025 liters. And if you're not sure about that, you can always work it out. right? There's 1,000 mils in a liter, 0.025 liters. So we 0.18 times 0.025, 4.5 times 10 to the negative 3. So now we just have to convert that into grams. And we'll have our answer. So bromine is about 79.9, hydrogen around 1.01. About 0.36 grams of HBr. So how many grams of HBr and 25 mils of aqueous 0.18 molar HBr? All we did is we set up the big M expression, we solved for moles of solute, and then we converted to grams. So this is so we first found the moles of HBr, and then here we converted to grams. So we'll do that first, do that second. So that's a two-step problem. Fructose, or sugar, occurs in honey and fruits. It's the sweetest sugar. It's nearly twice as sweet as sucrose. How much water should be added to 1.75 grams to give 0.125 little m? That's molal. How much water should be added to 1.75 grams of fructose to give 1.125 molal solution? Okay, let's set up the little molality equation, not molarity, molality. Moles of solute over kilograms of solvent. So instead of writing solute, right? Instead of writing that, what is the solute? It's that fructose. It's kind of easier, I think, if you do that. Instead of writing the word solute, and instead of writing the word solvent, don't write the word solvent. Instead, just write what it is, and it's water. Okay? So that means little m, they said, is 0.125. Moles. Let's see. Now they said that we have 1.75 grams of fructose of that C6H12O6. So we got to do some converting here, right? Before we can plug into our molal equation. Okay, how many grams of that stuff in a mole? And that's what we'll plug in. That's what we'll plug in right there. So 12.01 times 6 plus 1.01 times 12 plus 16 times 6. I get about 180.18 is the molar mass of fructose. About 9.7 times 10 to the negative 3. Okay, so 9.7 times 10 to the negative 3 moles. Okay, divided by kilograms of water. So we just have to solve for kilograms of water. And we'll have our answer. Well, in the wrong units, but pretty close. So our kilograms of water, right, would be 9.7 times 10 to the negative 3 divided by 0.125. Right? So you have to just go along the diagonal and switch those two. 0.077. Okay. Oh, they didn't even care about the units. Just said how much water. So we can just leave it in kilograms. We're done. Caffeine is a stimulant found in tea and coffee. A sample of the substance was dissolved in 45 grams of chloroform. How many grams of caffeine were in the sample? So again, we've got a molality equation. Little m would be the moles of solute, and that's that caffeine, C8H10N4O2, all over kilograms of solvent. What's the solvent? Chloroform. Okay. And what they're after is how many grams of caffeine are there. So can you see the game plan? Right? We're going to solve for this. And convert to grams. Okay, because we know everything else. We know that it's 0.0946 molality. We know that, well, we don't know the kilograms, but we know the grams of the solvent. But that's the same as 0.045 kilograms. You moved over 3 places, so we can find the moles of the caffeine. Right. This is on the bottom, so you just have to move it up to the top. So we'll end up with 0.0946 times 0.045. And we'll have our moles. About 4.257 times 10 to the negative 3. Okay, so now we just got to convert that into grams. We're talking about moles of what? Moles of the C8H10N4O2. So we've got 8 carbons. 8 times 12.01 plus 10 times 1.01 plus 4 times 14.01 plus 2 times 16, about 194.22. About 0.827 grams of caffeine. Which of the following ions would expect to have the greater energy of hydration? In other words, which one is better hydrated, more strongly hydrated? Well, just go by charge. What mass of solution containing 5% potassium iodide contains 258 milligrams of potassium iodide? So remember the milli is milligrams. So we'll have our percent equation, go back up and identify it. Mass percent equals mass of solute over total mass of solution times 100. Whoop. Mass solute over total mass. Remember, it was better not to write the word solute too, so we'll put in what it is. Potassium iodide. Oh, forgot about my 100. Okay, so the mass percent would be the 5. Okay, what else do we know? We know that we have 258 milligrams of potassium iodide. So there's two ways you can go about that. You can just recognize milli as 10 to the negative 3. So you could write that as 258 times 10 to the negative 3 grams of Ki, because that's what milli means. Or, right, you could work it out. 1,000 milligrams gram, move it over 3 places, 0.258 grams. Okay, but either way you get the exact same answer. Let's use this one. Over the total mass of solution. So we have to solve for that total mass. Again, just get used to moving stuff around that diagonal, right? Move that to the top, recognize the diagonals. We'll move total mass to the top, bring 5 back down to the bottom on the other side, and we'll have our answer. .258 divide by 5 times 100, about 5.16. Okay. So the thinking here is that we pretty much have 4 ways to express the concentration of a solution. I'll give you these equations. You just have to know how to use them.